Good morning, students. In the today's video, we'll discuss about the DSP processor architecture. So, in the third unit, we are having the architecture of the DSP processor, and also means architecture. In under the architecture, we'll study about the what are the parts which are integrated as a part of the DSP processor. Because as I told you that the DSP processor is quite different compared to the microprocessor. In the microprocessor, we don't have any memory devices, all those things as a part of the IC itself. But in case of the DSP processor, we are having the memory devices along with some other peripheral components like time delay generator and what we say that clock generator, time delay generator, host port interfacing, serial port communication, parallel port communication. Everything is there as a part of the same IC. That's why I can say that the DSP processor is quite different from the micro normal general purpose microprocessor. And also I told you that the main intention of the DSP processor is to process some what is it the unlock signal information. Okay, now the main intention of this particular DSP processor is to process the unlock information. Mostly, we are using the DSP processor. Okay, so here in the DSP processor, we are having the different types of architectures. Means different types of series which are there from the manufacturer, which is a Texas Instrument. We are having the different manufacturer who are manufacturing the what is it this particular DSP processor like Texas Instrumentation and Motorola company. Different manufacturers are there who are what is it designing this particular ICs, the DSP processor ICs. Okay, so as per our syllabus, we are going with the Texas Instrumentation DSP processor. That too, under the Texas Instrumentation, we are studying about the TMS 320C 5X family. Okay, so we are going to study about the TMS 320C 5X family. Here's my cursor. Should be the blue, right? So we are studying about the TMS 320C 5X family. 5X family. Okay, so this TMS 320C 5X family we are studying as a part of in our academic year. So in the third unit, we'll study about the architecture of the TMS 320C 5X family. But as I told you that there are different what is generations are there in the TMS 320 series. So those generations are displayed on the screen. Okay, so these are the different generations which are there from the TMS 320 C5 320 family, TMS 320 family. Under that, we are studying about the C5X generation. Under that, we are studying about the C5X generation. And yeah, we are having some coding conventions when you are going to study about a particular IC. Actually, we are studying about a particular IC, that is a DSP processor IC, which is a TMS 320 C5X. So here, this particular phi is indicating, this particular C is indicating that this particular TMS 320 C5 320, this particular TMS 320 microprocessor is designed using the CMOS technology. That is the main intention of the using the C. Okay, now, so CMOS technology is used in designing the this particular series, which is a TMS 320 C5X family. Okay, now, and this particular in this particular C means the using the CMOS technology, they have designed the TMS 320C family, TMS 320 family. And also, if at all we have the series like this, means in place of the C, if in place of the C, if we have the E. Okay, now, so let me go back to the C only. So this particular TMS 320C 5X family means say this family is designed with the help of the CMOS technology, and and also the normal ROM device is used as a permanent memory. ROM, normal ROM is used as a permanent memory. But in few series, if you are go through this particular TMS 320, you will come across in place of C, you will come across one more letter called as a capital E. In place of C, one more letter, you will come across one more letter called as a capital E. So if you are having the TMS 320 E 5X, TMS 320 E 5X, which means in place of the ROM. Okay, now so we are using the means this particular TMS 320 E5X family is using the EEPROM memory as a permanent memory instead of the ROM. EEPROM memory is used as a permanent memory. Okay, so means when we are having the series naming, so if you analyze more in detail, then for each and every letter there is a specific meaning followed by the manufacturer while designing a particular series of that may be the microprocessor or that may be the DSP processor or whatever the ICs we are having. Okay, now so there are some what is it the there is some intention is there which is representing something different compared to the normal case. Okay, so the next case is if we don't have anything, means if we don't have TMS 320 C5X or the E5X, and we are simply having the TMS 320 325x, means we don't have any letter between these two, means after the 320 we don't have any letter and we have only the series, then it is indicating that this particular TMS 320 DSP processor is designed with the help of the NMOS technology, means they have used the NMOS technology to design this particular what is that DSP processor. Okay, now so CMOS is a one kind of technology and NMOS is another kind of technology. Okay, now we are having the MOSFET now. So same MOSFETs are used in designing the microprocessor, but we are not here to discuss more detail about what exactly the CMOS technology and the NMOS technology. Okay, now so this is about a brief on the series number, a brief note on a particular series number 3 TMS 320C 5X family. Okay, so here yeah, let me go to this one. Yeah, as I told you that the TMS 320 is a microprocessor series, that is a DSP processor series. What is that? Introduced by the Texas Instrument company. So this manufacturer, what he's doing is he has introduced so many series in the DSP processor, that in the TMS 320. All these are the preceded with the TMS 320. TMS 320. Okay, so first generation means the series is C1X, 2X, 2XX, 5X, 54X, and the future. These series are called as a fixed point DSP processors. These series are called as a fixed point DSP processor. And another one is called as a C3X and C4X, are called as a floating point. What is that? Floating point DSP processor. Fixed point DSP processor means this particular DSP processor is not dealing with the floating arithmetic operations. It is working only on the fixed point values, fixed values. Okay, means the results are not in the fractional format. Okay, now so that is what the followed by this particular series. And the floating point operations, whatever the floating point operations we are expecting from the DSP processor, all those things are done in the floating point DSP processors. Okay, now so in this series, in the floating point DSP processor, means these processors are taking the responsibility to perform the floating point arithmetic operations also. Here we are having the results are the operations in the fixed point values like integer values, but here we are getting the float values also. Okay, now so the series which comes under this one is a C3X and C4X. Okay, so here different series are having the different applications. Okay, now so means we can't use a particular a particular DSP processor for all kind of operations, like using that this particular one for taking the photographs, means in the cellular phones, in the what is it, in the cameras, all those things. Means only one kind of series is not useful for all applications in TMS in DSP process. So they are meant for means each series is having a specific operation, a specific kind of application. So that's why we are having the different types of series in the TMS 320. Okay, now so the next one is a multiprocessor, and this particular multiprocessor means the name itself says that we are having the multiple processors inside it, and this particular processor takes the responsibility to perform multimedia applications. Okay, now so it is especially used in the multimedia applications and the 3D applications. Okay, so here if you see these series, when we are having different types of series from a particular manufacturer company, what they'll do is they'll go for supporting the instruction set, means whatever the instruction set which is written for me, when we are taking the advanced process or the different series of processor, obviously we may have the additional instructions. So what I mean to say that if you are taking the C1X, then whatever the instructions which are there in the C1X, or whatever the programs which are executed by the C1X, all those programs could be executed by the C2X. Okay, now So whatever the programs which are written for the C2X could be executed by the C2XX. Means here series DSP process are executing the older versions of the DSP process. Older versions, whatever the applications you have written for the older versions, they are supporting those applications also. Okay, now so that is the advantage of this particular TMS 320C. This particular TMS 320 family series coming from the Texas Instrument. Okay, so means if the code is written for the lower version, then the higher version get executes that particular lower version code, but the code which is written for the higher version could not be executed by the the lower version, because the instruction set may differ for the compared to the lower and there is a older and a new version. Okay, so the instruction set may be differ between the newer and the older versions. Okay, so that's why whatever the new version DSP process we have, all those processes are supporting the older version programs or the codes which are written for those specific series. Okay, so these are the different series coming from the TMS 320 family, and this one is performing the fixed point of arithmetic operations, and this one is performing the floating point arithmetic operations. And here we are having the multiprocessor, because in order to perform the 3D kind of operations and multimedia applications, we can't go with the one single single processor which is performing the digital signal processing. We should have the multiple one. Okay, so that's why we are having the multiple process. And if you want to know the these series, what kind of operations these fixed point series are doing, and what kind of operations the floating point processors are doing, and what kind of operations the multiprocessor DSPs are doing. Okay, now if you want to know that one, we'll go for that particular specific thing. I think I have given this particular document in the group. Okay, you just follow that one. So as I told you that we are having the new this version, the C1X 2X family. All these are the basic versions of DSP processor, that is a TMS 320 family. These are especially used in the toys hardware, that is hard disk drivers, modems, different types of applications. So these are the different types of applications which are supported by the first generation family. And C for 3X, 5X, and 6X, all these comes under what the floating point arithmetic operations, and they are supporting the means these are the different applications of each and every series which are coming from the TMS 320 family. Okay, TMS 320 family. And now let us go for the internal architecture of the DSP processor. Internal architecture of the DSP processor. So before going to the internal architecture and means in detail explanation of the internal architecture of the DSP processor, when you are taking a particular architecture, there are two types. The architectures based on the designing of the architecture of a particular processor. Sima, this explanation is applicable for the DSP processors, microprocessors, as well as the microcontroller. Depending on the designing of a particular architecture, there are two types of architectures. Okay, there are two types of architectures. One is the Harvard architecture, and another one is a Van Neumann architecture. Wait a minute. I'll take this one. Oops, not like that. Okay, architecture. So there are two types of architectures. One is the Harvard architecture, and another one is the Van Neumann architecture. Okay. So what exactly the Harvard architecture and what exactly the Van Neumann architecture is a question. So here, when you are taking the microprocessor, I'm assuming that this is a microprocessor. Okay, this is a microprocessor. That may be the DSP processor, or that may be the normal 8086 microprocessor. That may be the microcontroller also. But here we are means the architecture based on the designing of the architecture. The architectures are classified into two types. There are two types of architectures. Okay, so one is the Harvard architecture, another one is the Van Neumann architecture. Now, based on what we can comment that a particular architecture is a Harvard architecture, means a particular microprocessor architecture is following the Harvard architecture, and a particular microprocessor architecture is following the Van Neumann architecture is a question. Okay, So here I'm assuming that this is my microprocessor. Okay, now don't get confused. The same thing is applicable to the DSP processor also, but as we are aware of microprocessor, I'm just taking the microprocessor. Okay, so DSP is nothing but it is a microprocessor only, but with additional features, right? So and after that, what I'm doing is I'm having the means I'm using the separate memory devices for the program as well as the data. Okay, so I'm assuming that it is a data memory. Okay, so I'm assuming that it is a data memory, and I'm assuming this one as a program memory. So one is a data memory, another one is a program memory. And now if I'm having the separate buses, if I'm having the separate buses, okay, now separate buses, there is the address as well as the data bus. If I'm having the separate buses for the program memory as well as the data memory, I'm not showing the direction of the data flow, so I'm just showing that there is a separate buses. Okay, so we have the separate bus for the data memory and we have the separate bus for the program memory. Okay, means if a particular microprocessor architecture is providing, architecture design is providing the separate buses for the data memory as well as the program memory, means separate address as well as the data bus for the data memory, separate address as well as the data bus for the program memory. Okay, separate buses are there. Then this kind of architecture is called as a Harvard architecture. This kind of architecture is called as a Harvard architecture. Okay, so the next case is a Van Neumann architecture. Okay, Van Neumann architecture. So in the Van Neumann architecture also we have the means we have the program memory as well as the data memory, but we may use the same memory as a program as well as the data. Okay, but we least bother about whether we are using same memory or the separate memory for the program data. But the thing is, here in this case, what we do is in this case it is a microprocessor. It is a microprocessor, and here I'm using the common bus now. I'm using the common bus for program memory as well as the data memory. I'm using the common bus. I'm using the common bus for the program memory as well as the data memory. Program memory as well as the data memory means I don't have any separate bus. I have the common bus. I have the common bus. Okay. So I'm assuming this one is a data memory, and this one is a program memory. Okay, one is a data memory, another one is a program memory. Here we are having the common bus. Okay, so this kind of, if at all that architecture design, a particular microprocessor architecture design is providing the common bus means a common bus for the data memory as well as the program memory. Then that architecture is called as a Van Neumann architecture. That architecture is called as a Van Neumann architecture. One is a Harvard architecture, another one is a Van Neumann architecture. Harvard architecture is nothing but we have the separate buses. We have the separate buses for the data memory as well as the program memory. But in case of the Van Neumann architecture, we have the common bus for both program memory as well as the data memory. I may represent this particular common. Oh, sorry. I may represent this one. No. Okay, so we have the data memory and program memory now. For simplicity, what I'll do is I'll take one line like this and I'll use this one. So it is only for remembering which architecture is following what kind of structure. So if you see this one, it is a common bus. I may represent like this. Okay, now it is only for remembering. It is a thumb rule. In order to create the thumb rule, I am taking this one. So it is a common bus. The red color and the blue color both are indicating the bus only. They are the common. But here, if you see this one, in the Van Neumann architecture, we have the VNA. If you invert this one, if you invert the V like this, then we have the common bus. Harvard architecture, if you take only the perpendicular line, means you are not getting this one, you are not taking that, then it looks like Harvard architecture. Means if I am taking what is that a line, parallel line, then it is touching like this, so it is forming the H. So it is a Harvard architecture. So in order to remember in thumb way, I'm just giving this format. Yeah, I'm just giving this one. Okay, in order to remember this architecture, so means which architecture is following the what kind of configuration. So Harvard architecture is providing separate address as well as the data buses for program as well as the data memory, and here Van Neumann architecture is providing the common buses for both the program and the data memories. Okay, So that is the difference. But what is the advantage of the Harvard architecture means, as we are having the separate buses, then the execution speed is more in the Harvard architecture case compared to the Van Neumann architecture, because as we are having the separate bus for the data memory and the program memory, at a time we can perform the two operations. Means at a time we can perform the operation on the program memory, means we can ask the microprocessor to read the output from the memory. At the same time we can perform some arithmetic operations on the data memory. Okay, we can perform some arithmetic operations in the data memory. So that's why it is called as a parallelism, improving the parallelism of operation. So when we are having the parallelism, then the execution speed is more. But in this case, it is not like that. If you are performing the operation with respect to the program memory, you can't access the operations related to the data memory, because only one bus, a common bus, is allocated for both memory devices. So that's why the execution speed is less in the Van Neumann architecture compared to the Harvard architecture. And we have one more thing called as a, I think I would have explained this point, called that is a RISC processor and the CISC processor. RISC and the CISC processor. But I'll explain that one once the means the situation demands. I'll explain that one also. Okay, don't worry about it. So here Harvard architecture and the Van Neumann architecture. So here whatever the DSP processor we are having, this particular DSP processor is supporting the Harvard architecture. This particular DSP processor is supporting the Harvard architecture. Wait a minute. It is supporting the Harvard architecture. This particular one is supporting the Harvard architecture. So that's why I explained that particular concept. Okay. So now inside the this particular DSP processor is providing the, as it is the Harvard architecture, as it is supporting the Harvard architecture format. Then it is supporting that it is providing the different buses. So the bus structure of the DSP processor. So in the 8086 microprocessor, we come across only the two buses. One is the address bus and the data bus. But here in the DSP processor, we are having the four buses. In the DSP processor, we are having the four buses. So first bus is a program bus. Okay. Next bus is a program address bus. Next bus is a data bus. Okay. Next bus is a data read address bus. So PB program bus, PAB program address bus, DB data read bus, and DAB data read address bus. What is the program bus means? This bus takes the responsibility. So means for the program memory we have the two buses, for the data memory we have the two buses. Okay, and they are the separate buses. Okay, they are not common, they are the separate buses. So the program bus takes the responsibility to carry the opcode as well as the immediate values. So opcode as well as the immediate values. In order to carry this kind of information, the program bus is used. But if you want to access a particular memory location, so these are for carrying the opcode and the immediate operands. But this one for carrying the addresses to perform the read operation as well as the write operation. Means in which location you would like to write the information, and from which location you would like to read the information. For that you are supposed to provide the addresses. So those addresses are carried by the program address bus. Now coming to the data read bus. So the data read bus takes a responsibility to interconnect some of the CPU elements to the data memory space. So here we are supposed to discuss a little more actually. In the microprocessor case, whatever the microprocessor it is, it may be the 8085 microprocessor or 8086 microprocessor or the DSP processor, we are having one naming convention, regular naming convention called as the registers. Registers are nothing but what? They are the storage elements. Okay, they are the storage elements. Okay, so those registers are storing the information. Those registers are storing the information, and that information may changes during the execution of the program. And one more thing is, I would have explained this point in the 8086 case. Register is nothing but means accumulator is nothing but it is a name assigned to a memory location. It is a name assigned to a memory location. When the microprocessor, whatever the microprocessor it is, 8085, 8086 or the DSP processor, when the microprocessors are designed, they are introducing the different types of registers. Means each microprocessor is having the separate registers are there. So those registers are names assigned to the memory location. Register is nothing but it is a name assigned to a memory location whose value may changes. Or variable is also the same thing. Name assigned to a memory location whose value may changes during the execution of the program. Okay. Now, so here when you are taking the accumulator, I think you would have seen this particular accumulator case in the 8085. In the 8085, we are having the 8 registers are there. 8 registers are there, and eight registers means we are having the register A, B, C, D, E. Okay, now H, A, B, C, D, C, D, H, L pair. I think so. Yeah, A, B, C, D, H, L pair. Okay, so after that we're having the what is it, other registers also inside the 8085 microprocessor. But the thing is, why I'm taking this explanation is those registers are having the specific address map. Means actually those registers are accessed by the microprocessor with their addresses, not with their names, because the microprocessor don't know, or it is not aware of the register names. It is not aware of the names. It is aware of only the addresses which are assigned to the that particular register. Means the registers are accessed by the microprocessor with their addresses, not with their naming conventions. Okay. So here the point, it interconnects the various elements of the CPU to the memory space is nothing but whatever the registers which are there in the CPU, that is the DSP processor, those registers are mapped to the memory locations which are there in the data memory. Mapping is nothing but assigning some address in the memory location. But whatever the addresses which are assigned for the registers, they are the fixed addresses. They are the fixed addresses. And those addresses are nothing but they are the part of the memory device only. The registers are having some addresses, and those addresses as a part of the memory only, so, and that too they are having the predefined address. Variable is nothing but whose address is changing during the execution of the program. Okay, whenever you are trying to execute the program, every time the variable is assigned with the new addresses. But in case of the registers, the addresses won't be changed. They are the fixed one, but they are mapped to the memory location. But when the architecture is designed, some of the manufacturers, what they will do is they will give the hardware registers. They give the hardware registers. The hardware registers means whatever the flip flops. I think you would have seen in the what is that digital electronics. You would have seen the construction of the what is that register. Okay, now construction of the register. So those registers are constructed with the help of the flip flops. Okay, now. So if at all the flip flops are arranged and a register is constructed, they are called as the hardware registers. But there are some other kind of approaches there in designing the registers. There is nothing but having the naming convention, mapping those registers to the memory location. Either we have the hard-coded registers as a part of the architecture, or we may have the mapping those register addresses directly into the memory space. Okay, now directly into the memory space. So here the DB bus takes the responsibility to map the register names to the memory locations, and they are the fixed memory locations now. And after that we have the data read address bus. This particular bus takes the responsibility to carry the addresses related to the data memory. Address related to the data memory means to read the data from the so and so memory, or to write the data into the so and so memory. So those addresses are carried by the data read address bus. So these are the 4 different types of buses which are supported by the DSP processor, Okay, so now let's go for wait a minute. Let's go to the architecture of the DSP processor. I think this one is not good for looking into the architecture. Wait a minute, I'm having a slide for that, because it won't show the complete figure. So this is what the architecture of the DSP processor. Okay, now. So the internal architecture of the DSP processor. One is a CPU block. Another one is a memory block. Another one is a memory block, and we have the buses. Okay, now they are not showing the what is the different types of buses in order to reduce the complexity of the diagram. They simply shown that there is a data bus and another one is a program bus. That's it. Okay, now. So the memory and the CPU. As I told you that we are having the on-chip memory devices. we are having the on-chip memory devices as well as we are having the on-chip peripherals. Memory devices can also be called as a on-chip peripheral, and another kind of devices are there. They are acting as a peripherals like a host port interface, timers, serial communication port, and all those things are called as a on-chip peripherals. They are the on-chip peripherals because all these components are available in the same IC. All these components are available in the same IC. That's why they are called as a on-chip peripherals. Okay. So as I told you that we have the memory device. Okay. We are having the on-chip memory in the DSP processor. So different types of on-chip memories are there in the DSP processor. One is a program memory. Another one is a data memory. Okay. Now, so data memory means it is a single access RAM. It is a data. This particular SA RAM, which is a single access RAM, may be used as a data memory or the program memory, and we are having the DA RAM, dual access RAM, may be acting as a data memory or the program memory. We'll come to this particular on-chip memory concept separately. Okay, now we have one topic on this particular on-chip memories. Okay, now, so don't worry about it. But in brief, just remember that we have the program memory, and these are the, if you see this one, for each series of the TMS 320 family, we are having the separate sizes. Different sizes are there in different series. Okay, now the program memory size is different in different series. Okay, so in the data memory also, which is a single SCA RAM, is nothing but the single access random access memory. Okay, now it is a single access one. SA means single access one, and it may be act as a data memory or it may be act as a program memory, but it may not be act as a both. Means either it may be configured as a data memory or maybe configured as a program memory, but it cannot be used as a data as well as a program memory. But if you come to the DRAM, you may configure this memory as a program memory or the data memory. Okay, now you may configure this one as a program memory or the data memory or both. Means this memory can be act as a program as well as the data, but this memory can be act as a either program or the data. So that's why it is a single access and it is a dual access. And this particular dual access memory is divided into the blocks format now, B0, B1, B2. And if you come to the ROM, the memory is divided into the page format. The memory is divided into the page format. Okay, now. So in case of the 8086 microprocessor, memory is divided into the segment format. But in case of the DSP processor, memory is divided into the page format, and some of the memory devices are divided into the blocks format. We'll go for the in detail explanation under the on-chip memories topic. Okay. So the next case is in the CPU block, central processing unit block. We will study about the parallel logic unit. What is the use of the parallel logic unit? What is the use of the CALU block? That is the central arithmetic logic unit. We have the central arithmetic logic unit. Okay, now. So the next case is the memory mapped registers concept. ARAU, auxiliary register and arithmetic unit block, program controller, program counter, status registers, hardware stack. Hardware stack means, as I told you, that the stack is nothing but, in general, stack is nothing but it is a part of the RAM memory, or I can say that it is a special purpose memory. A part of the RAM memory is used as a stack, and it is used during the execution of the program. Okay, now. So in general, in normal microprocessor, RAM, a part of the RAM is assigned as a stack memory, is treated as a stack memory. But in case of the few architectures, some memory is there as a part of the architecture only, and it is used as a stack. If that particular stack memory is not sufficient, means whatever the memory which is there as a part of the architecture itself, if that one is not sufficient, then they'll go for the making use of the RAM memory as a stack area. Okay, now. So that's why they are called as if at all the stack area is there as a part of the architecture, that memory is called as a hardware stack. Don't get confused. It is a stack memory only, but the memory which is used for stack operation, it is there as a part of the microprocessor itself. Okay, if it is not there, then a part of the RAM memory is assigned for the stack operation. Stack operation is nothing but push and pop operation, and it is especially used in the during the execution of the program. It is used for holding the values. Okay, now we have seen that one, right? So the next one is the address logic generator and the instruction register. Okay, so these are the different blocks which are there from the CPU. The next on-chip peripherals, all these parts, whatever the thing you are seeing right over here, these are the on-chip peripherals. Serial port 1 means we are having the serial port communication lines, we are having the time division multiplexing lines, and we are having the buffered serial port operation, and we are having the timer, we are having the host port interface, we are having the test evolution. Means all these components will study in brief under the on-chip peripherals concept. Okay, under the on-chip peripherals concept. Are we clear? So this is about your DSP microprocessor architecture. This is about your DSP processor architecture, microprocessor architecture. Okay, now it looks like a complicated one, but it is very easy. Actually, the block is divided into memory and the CPU. Memory and the CPU. Okay, so let's go for realizing one by one. So first concept which we study about the CPU is a CALU block, which is a central and arithmetic logic unit block. CALU block, central arithmetic logic unit block. Okay, now so what I'll do is I'll take the PDF from your textbook. I'm following your textbook only. I'm directly giving the explanation. Okay, so central arithmetic logic unit. I think in order to show all these things, Sima, as I told you that I'm using this is a what is a TMS 320 320 family user guide, ma. So if you want, I'll show this one. Yeah, yeah, it is a user guide. I'm just following this one because in order to give the elaborated explanation, I'm going with the user's guide because whatever the textbook which is written by the Venkataramani and Bhaskar, and they have taken the information from this particular user guide only. Okay, they have taken this one as a reference copy, and based on that, how much you need, that explanation is that much only they have what retrieved and placed in the textbook. Okay, but here are somewhere whenever I need more explanation for you people, then I'll take the information from the TMS 320C5 from this particular user guide only. Okay, now so let us go for the CALU block. We are having the different types of applications. I think I would have transferred you the PDF format. Wait a minute. I think it's a 40 minutes over. No time to get up. That's the biggest problem. Come on, man. Oops. Separate indexes for separate one. Okay. First one is a CALU block. Yeah, in short. Okay, in short, you just note down this point. I'll give the explanation. Okay, so in short, central arithmetic logic unit, which is nothing but the CALU. So this particular CALU is performing the 2's complement arithmetic operations. Okay, so means it is performing the two 16-bit numbers, multiplication between the two 16-bit numbers, and these two values, whatever the 16-bit numbers, two 16-bit numbers we are using, those values are represented in the 2's complement form. Those values are represented in the 2's complement form. Okay, now, and inside the CALU block we have the 32-bit arithmetic and logic unit. So means if we have the 32-bit arithmetic logic unit, means it is able to perform the 32-bit arithmetic operations, 32-bit arithmetic operations, addition and subtraction operation. And this block is also having 32-bit accumulator, 32-bit accumulator buffer register, and we have the product register also. Okay, now so the product register, accumulator buffer, accumulator. These three are the 32-bit registers, now. Okay, now these three are the 32-bit registers, and product register is used for holding the result of the multiplication. The product register is used for holding the result of the multiplication. What kind of multiplication this block is able to perform? 16-bit multiplication, and whatever the numbers which we are using in this particular 16-bit multiplication, they are represented. Those values are represented in the 2's complement form. Now, when you are taking the multiplication between the two numbers, we call that one of the operand is a multiplicand and another one is a multiplier. Okay, one of the operand is a multiplicand, another one is a multiplier. Okay, so multiplicand is nothing but this particular multiplicand. So here I'm assuming this is a 116-bit number and it is another 16-bit number. Now I'm assuming that this is a multiplicand. This operand means two operands are there, and each size is a 16-bit word, and this is a 16-bit operand, which I'm naming it as a multiplicand. And this particular multiplicand 16-bit number should be there in one of the 16-bit register called as a temporary register 0. one of the 16-bit register called as a temporary register 0, and it is a 16-bit register which is used for holding the multiplicand value which is used in the multiplication. Means in these two operands we are trying to perform the multiplication between the two operands. In these two operands, one of the operand is called as a multiplicand, another one is called as a multiplier. Multiplicand operand, which is a 16-bit word, should be there in the 16-bit temporary register 0, should be there in the 16-bit temporary register 0. And another one is a 16-bit multiplier is there. So 16-bit multiplier can be represented by any one of the addressing modes. That may be the immediate addressing mode, that may be the register addressing mode, indirect addressing mode, whatever the addressing mode. One of the addressing mode is used to indicate the what is that 16-bit multiplier. One is a multiplicand, another one is a multiplier. So multiplicand should be there in the temporary register 0, multiplier should be there in multiplier is represented using one of the addressing mode which are supported by the DSP processor, Now the thing is, after performing the multiplication between the two 16-bit number, so the result is what 32-bit number. The result is a 32-bit number. Why I'm saying that one is, if you are taking the single digit decimal number, it's a 9. Maximum number is what 9. 9 into 9. If I'm performing the multiplication between the two single digit maximum numbers, then obviously it is a 2-digit number. Single digit number multiplication means it is a 2-digit number. In the same way, when you are taking the maximum 16-bit number and the maximum 16-bit number, the product of this particular 16-bit multiplication gives the 32-bit result, and that particular 32-bit result will be stored inside the product register. The result of this particular multiplication is stored in the 32-bit product register. It is stored in the 32-bit product register. Abu clear? So the next case is, whenever we are trying to perform the arithmetic operations like addition, subtraction, all those arithmetic operations, addition, subtractions. I'm not considering the multiplication because the multiplication is one of the operand is there in the TREG. Okay, so in arithmetic operations, the accumulator register is the one which is holding the value one of the operand. Means in arithmetic operations, addition, subtraction operation, one of the operand should be the accumulator. And the result of that particular operation will be stored inside the accumulator only. It will be stored inside the accumulator only. If you want to know that one, then let me take this one. This is from your textbook, right? So that was from the user guide. So this is from your textbook. Okay. So when you are performing the multiplication between the two numbers, temporary register is used, temporary register 0, and the another one is represented with the another addressing mode. But in addition subtraction case, one of the operand should be there in the accumulator. And we have one more register called as accumulator buffer. Now this accumulator buffer is used to hold a copy of accumulator value temporarily. Okay, so accumulator buffer is used for temporary storage of the accumulator value only. Means a copy of the accumulator value is there in the accumulator buffer, or I can say that accumulator buffer is carrying the shadow of the accumulator. Okay, now so this is the accumulator buffer. And one more thing is, this particular CALU is having one more feature called as a barrel shifter operation. Okay, now so barrel left shifting, it is just like a shifting operation only, but the barrel shifters are designed with the help of the combinational circuits, not the sequential circuits. Okay, now barrel shifters are designed with the help of the combinational circuit, not the sequential circuit. We list by about those definitions. We are only by about the CALU block is supporting the barrel shifting operation. Okay, now barrel shifting operation, and those barrel shifting shiftings are the 16-bit shifting. Okay, now 0 to 16-bit shifting. Those barrel shifters are maybe the left barrel shifter or the right barrel shifter. It is supported by the CALU block. Okay, now, but how many number of bits should be shifted either to the left side or right side? How many number of bits should be shifted either to the left side or right side? That is indicated by one of the 5-bit register called as a temporary register 1 register. Means temporary register 1 is a 5-bit register which is used for indicating the count value. So means this register is showing the count value. That count is nothing but how many number of times the shifting should be done. It may be the left shifting or right shifting. How many number of times that shifting should be done, that is indicated by the temporary register 1, temporary register 1, whose size is a 5-bit size. Whose size is a 5-bit size. Okay. So I think the video is the very lengthy one. I'll make another video. I'll continue the topic in the explanation in the another video. So this is all about your what is that DSP processor and the CALU block. So in short, CALU block is containing the accumulator register, accumulator buffer register, product register, and it is supporting the 16 by 16 2's complement multiplication. Means 16 by 16 multiplication only, but the operands are there in the 2's complement form. Okay. And we are having the barrel shifting operation, left shifting as well as the right shifting operation. Those are supported by the CALU block. Okay. So this is all about your DSP processor. We'll continue in the next class with the remaining blocks. Okay. Now I thought that I'll finish up this, but the time is exceeded. 10:53 means 10:55. 10:55 means 15 minutes. It is a 45 minutes. 45 minutes class. Okay. Okay. We'll continue with the ARAU block and other blocks with the in the another video. Okay, don't worry. If you have any queries regarding this topic, let me know in the group.